we starting? Okay. So let's see. Last time we had basically found that the S operator was a time-ordered product of e to the minus I, an integral with interaction in the interaction picture, and taking the limits to infinity, this is the integral from minus infinity to plus infinity. And this gives the matrix element, the same matrix elements as U, the time evolution operator, which would be e to the minus I, basically 2t where as t goes to infinity. These would give the same matrix elements between eigenstates of the free Hamiltonian. And so this is what we use, and what we do is we expand this so that it looks like 1 minus I over h bar integral of vi of t dt, and vi of t differs from v of t by e to the, and now I forget the sign, damn it. Go way back in these notes to get the sign. E to the minus I h0 t over h bar e to the I t to the I h0 t over h bar. Okay, so that's a review of what we did last time. Now, this time I want to talk about quantum field theory and quantizing the electromagnetic field, and looking at the interaction between the electromagnetic field and an atom. And so that would be that's basically the topic here. One of the difficulties is converting my old notes, which were in unrationalized heaviside Lorentz units, to SI units. And if you look at the online notes, you see that I only got through 7 pages of that. Let me first of all say what it is that's going on. You see, in other words, what's the idea behind quantizing the field? Basically, you have a quantum system with many Qs sub i's. Then you find your P sub i's and you say that Qi commutator Pj is delta Ij, and because this comes from basically a Lagrangian, and you say Pj is partial of the Lagrangian with respect to Qj dot. So that's the system that you set up. And in the case of, okay, so you can imagine, instead of having just 3 Qs and 3 Ps for an ordinary particle in 3-dimensional space, you can imagine having a field operator, phi, in other words, Qi, is going to be some field operator at a point xi at a time t. That would be Qi of t. And so you imagine for each point of space you have a field operator, and that gives you your Q. And then depending on what your Lagrangian is, a typical Lagrangian for Lagrange density for a scalar field is a half phi dot squared minus a half grad phi squared minus a half mu squared phi squared. This is a Lagrange density for a free field. And you then would say that your conjugate momentum, so the Pj of t, would be the partial of Lagrange density with respect to phi I dot, and it would be phi I dot at xj and t, say, and this then would give you phi dot at xj and t. So these would be your two canonically conjugate variables, and then what you want to do is say is imitate this. So you want to say that phi at xi at time t and phi dot at xj in time t as a commutator that's I h bar, and now delta ij becomes delta q of xi minus xj. So that's basically the way you quantize a scalar field. This thing is typically called pi of xj and t, and so you could instead have in here pi of xj and t. And then you construct the Hamiltonian in the usual way. And the Hamiltonian then is an integral dq x of a half pi squared grad t squared over 2 plus u squared over 2 t squared. This thing being an integral dq x phi dot pi minus the Lagrange density. And if you use this identification, then you see you get this expression here. So that's the basic way in which one does the quantization, and in order to have things work out like this, you basically say that your field x of t, you can do it as a sum over modes k, and you then have some ak. Let's see, you might need to motivate this further. Well, let me just say that your field equation would come from Lagrange density, and you'd say that partial mu of partial L partial phi comma mu is equal to partial L partial phi, and in that case these derivatives here, this thing looks like minus d mu phi with a 1/2 apart from the mass term, and so what you find is an equation that's d mu phi is equal to mu squared phi, and I need a minus sign there. So that's your equation of motion. And so if you expand these things as a sub k times some mode, let us say, you can expand them in Fourier space ak dot x, but now this ak is an a sub k of t plus ak dagger of t, either minus r k dot x, and then because of this equation, you see that the field operator, if you apply this to, if you substitute this expression for the field into here, what you get is minus d mu on p then is a sum over k. This would be a double dot of k minus k vector squared a of k times c di k dot x, and then plus the complex conjugate term. So that would be the expression, and you want this to equal mu squared let me see if I have the signs right. Actually, I think I got the signs wrong. You want this to be mu squared p, and so that would mean we have, I'll get this one right in a second. Well, it would be mu squared times ak, and yeah, there's just an overall sign that's wrong. Yeah. Well, I guess I shouldn't try to do this without going slowly, step by step. Let's see. Yeah, this should be a plus. If that's a plus, then there's a minus here, and a minus there. So it looks like this. And so that tells you then that a minus ak double dot is equal to k squared plus mu squared times base of k. And this is what you want, because then you can say that the base of k is e to the minus I omega kt, and that will give you the equation omega k squared is equal to k squared plus mu squared. And so that's our expression then for the energy. I've unfortunately, in doing this, for some reason I decided that it would be pedagogically useful to do this without by departing from my notes, and so I've got H bars loose all over the place. Actually, K dot X is okay. I don't need an H bar there. In any event, one finds that that A has this time dependence, and so that's basically how you work out a scalar field. All right, so now we're going to apply this sort of approach to electrodynamics, which is more complicated. We start out with Maxwell's equations in SI units. There are two homogeneous equations. And two inhomogeneous equations. Curl B is mu0k plus E dot over C squared. And we introduce scalar and vector potentials. So E is minus grad phi minus A dot, and B occurs curl A. these two equations actually then imply these two equations. They imply the homogeneous equations. In particular, the divergence of the curl is 0, and if you take the curl of this expression, you get curl of E, then you get a B dot on the other side, and the curl of the gradient is 0. So this equation gives that one. These scalar and vector potentials form a Paul vector. The Paul vector is I use the Greek letter, a mu is the scalar potential over C, and then the vector potential. Now, a gauge transformation is a change a mu prime of x is the old a mu of x plus d mu lambda of x, where lambda is any scalar function of space and time, so any scalar field. And under a gauge transformation, so under E prime is equal to E, E prime is equal to E. So E and D don't change. So that's basically Maxwell's equation. Now what we do is we go to the Coulomb gauge, also known as the radiation gauge, del dot A equals 0. And just for completeness, let's use the gauge transformation to get there. We want 0 is del dot A prime, so that will be del dot A plus gradient lambda, and plus divergence of gradient lambda. And we want that to be 0, and so what we say is that del squared lambda should be minus the divergence of the old A. And so if we choose lambda as a solution of this differential equation, make a gauge transformation, the new equation, the new gauge field will be in the radiation gauge or the Coulomb gauge. Now, Gauss's law, which is over here, tells us that del dot E, and now the nice thing about the radiation gauge is that the divergence of E doesn't involve a dot, because A has no divergence. So this is just equal to minus grad squared phi, or Laplacian of phi, which is rho over epsilon 0, and then you can solve for that, and when you solve for that, you get phi of x and t equals 1 over 4 pi epsilon 0 and integral d cubed y, the charge density rho at y and t divided by the distance between the point of observation and the point of the charge density, well, which is all space. So that's phi, and this is something important has just happened, which happens in this Coulomb gauge, which is one of the reasons why it's a very physical gauge and nice gauge to work in. And it's that this phi has just become a dependent field, a dependent variable. It depends on the charge density. And so it's basically gone from there's no issue of quantizing phi, because phi is whatever rho is. And if we've got rho quantized, then that's what phi is. And if we if we were to do this in full detail and start with Lagrangian and construct the Hamiltonian in a canonical way, we would see at some point that we get a part of the Hamiltonian, the charged part of the Hamiltonian, would be an integral of rho of x, rho of y, p cubed x, p cubed y, over 4 pi epsilon 0 x minus y, and then an extra factor of 1/2 because we're counting the charges twice. So this would appear in the Hamiltonian, and in fact we'll see it show up later when we talk about the atom. Now, of course, the reason why this is a solution of this equation is that minus, let me just say that this thing is this grad school. This is divergence of grad, and this is often written as Laplacian. Minus Laplacian with respect to x of 1 over x minus y is equal to 4 pi delta cube of x minus y. So this into here gives us that, as you certainly know. Somehow I put us, so this. All right, well, once again in Coulomb's gauge, let's just look at this vector identity. Curl of the curl of A, which is of course the curl of B, is the gradient of the divergence of A minus the Laplacian of A. And of course in the Coulomb gauge, it's just minus Laplacian A. Coulomb's gauge. So, looking back at this equation, this thing here is minus Laplacian of A. So del cross B is minus Laplacian of A. And then one of Maxwell's equations, I'm going now to empty space, okay, so I'm setting J equal to 0. Del cross B is equal to E dot over C squared. But again, in empty space, B is 0 and E is minus A dot. So this is minus a double dot over C squared. And so that gives us the equation Laplacian minus second time derivative over C squared acting on A of x and t equals 0. So this is, of course, the wave equation, and that's the analog of this equation that we had for the scalar field of mass mu. When there's no mass, then this thing, you just have the second derivatives. That d mu is just this structure here, acting on the field of 0. So this is because the photon has mass 0. By the way, one thing that I should have mentioned here, one aspect of the Coulomb gauge that's unattractive. So I've said there are many nice things about the Coulomb gauge. There's one awkward feature of the Coulomb gauge. The awkward feature of the Coulomb gauge is that phi is related in the Coulomb gauge instantaneously to the charge distribution. The charge distribution at the same time, even when the charge distribution is far from the point X. So in other words, this phi is given by integral throw over all states at the same time. So charges in Andromeda count, because they're weighted by 1 over the distance. So they don't count much, and Andromeda is basically neutral, so it doesn't have any effect. But that's an awkward thing about this. Doesn't mean the theory is violates relativity. It just means that the gauge choice, del dot A equals 0, isn't a relativistically covariant choice of gauge. Okay, well, we don't need to knock ourselves out over that. Let me get back to these basic solutions. Here we have this wave equation. What's the simplest solution of it? Well, A of x and t can be just some A0 e to the I k dot x minus omega t, and then because then A double dot is equal to minus omega squared A, and Laplacian on A is equal to minus k squared A, and so the whole equation is minus k squared plus omega squared over c squared times A is equal to 0, and that just tells us that omega is equal to kc, where k is the length of the vector. So that's our relation. Now there's one more thing. We have this Coulomb gauge condition. So what does that tell us about this vector A here? Well, if del dot A is to vanish, del dot A, of course, involves I k dot A0 times this exponential. So that means that k dot A0 equals 0 in the Coulomb gauge. So A0 must be a vector perpendicular to k. All right, so now we're going to do box quantization. We're going to do volume L cubed. So the box of side L, and we want A of 0, well, there's no arrow on this. This is actually the number 0. X, Y, Z, T to equal A of L, Y, Z, T. And so forth for the other, the X, Y, X, for the Y and the Z directions. And what that means then is that A of X vector and T is some polarization vector divided by the square root of volume times EDI k dot x minus omega t, where k, the vector, is 2 pi over L times the vector of integers n1, n2, n3. And notice here that epsilon sub r of k dot k equals 0. So the polarization vectors have to be perpendicular to the 3 momentum. And these integers n sub I are plus or minus 1, plus or minus 2, etc. Of course, they vary independently. Okay, is any question about this? Now, in three-dimensional space, you have 3 orthonormal vectors. So one is k, the other 2 are epsilon 1, epsilon 2, so R goes from 1 to 2. And we might as well make them normalized, so ER of K dot ES of K is equal to delta RS, and K dot ER of K equals 0. So those are the polarization vectors. Now, if you take them to be real, and you can basically, most calculations assume that they're real, makes things a little bit simpler. The real ones represent linearly polarized fields. In general, though, they're complex. Okay, so what is our field? Doing this field quantization, then we have the sum over these different modes, sum over all k's being these things, these vectors. Then we have what we call a fudge factor, which is a normalization factor, which is 2 epsilon 0 v omega k. And all of that to the 1/2. I left out the 1/2 in the online notes for some reason. And then what we've got is epsilon sub r, the vector of k, k sub r, of k, and for some reason I put t back in here, but it seems to me this is kind of gilding the lily, but all right, I'll put the t back in for a moment. EVI k dot x plus e sub r star of k, a dagger sub r of k, and c e minus I k dot x. Okay, so that's the expression. But once again, we want it to satisfy the wave equation, which here is Laplacian minus the second time derivative over c squared, or 0 equals Laplacian a minus the double dot over c squared, and that gives you that a double dots of r of k and c is just minus kc squared a sub r k and c. And so this is e minus I omega k t a sub r. Well, which a's are k, simply. So in other words, a sub r k and c is e to the minus I omega t times that. We take that for the a, and so in other words, I suppose the way to do this is to edit with a race of e to the I k dot x minus omega t, and then over here. Okay, so that's our expression for the electromagnetic field, and how do we get the t? Now, if you're seeing this for the first time, there should be some questions. Okay, let me say that remember back here when I was talking about quantization in the very beginning, I said that what you want to do is you want to have phi with phi dot be something like a delta function. Okay. The way you get that in this particular case, it's a little more tricky in the case of the electromagnetic field because, first of all, it's in Coulomb gauge, and secondly, it's a vector field. What we will do is to impose these quantization conditions, a sub r of k. My goodness, I left out a dagger. A dagger sub r prime of k prime is delta sub k prime delta r prime. Remember, we're in a box. We're quantized in a box, so this is a discrete set of modes. These are then the commutation relations. A with itself, a sub r, a r prime is 0, and that implies, of course, a r dagger, a r prime dagger. So this is the key quantization relation. What this means is that if I remember correctly, it means that basically your AI, it turns out that the conjugate momentum to A is again essentially A dot, which is E, and you've got something like let me just call it pi j, which is related to E, is going to be I h bar, but now it can't be delta ij because these components aren't really independent because they have to satisfy the Coulomb gauge condition. So it turns out this is a transverse delta function. It's got to be transverse in the sense that, and in fact, I should put an ij on it. It's a transverse delta function because it has to satisfy del dot. This transverse delta function has to be 0. Anyway, leave that aside. Those are some technicalities that come up in the case of the electromagnetic field, which of course is the real case, and that's one of the somewhat embarrassing things about quantum field theory. The machinery goes through without any squeaks or bumps in the case of a scalar field. But as soon as you leave the simple case of a scalar field and try to quantize a field, there are theoretical subtleties that show up. Spin 1/2, spin 1, and so forth. And they're one sign, I think, that quantum field theory isn't the last word. There's something beyond it that we don't know about. Whether it's string theory, I don't know, but there's got to be something better than quantum field theory. All right. Anyway, but on the other hand, in quantum electrodynamics is extremely accurate, as you know. So let's appreciate it. Okay. Well, you remember back weeks ago, before we started perturbation theory, I discussed the charged particle in the electromagnetic field and the Hamiltonian associated with that, and so forth. So let's go back to that for a minute. What we have there is that the Hamiltonian is 1/2m P minus QA of x⁴ squared plus Q phi of x⁴. I'm leaving out spin for the moment. It turns out electron spin doesn't have a lot to do with at least the simpler calculations. If you want to add in spin, you can say minus Q over M S dot B of x and t, where x is equal to And this Q phi, this term here, is actually the term that I said arises from, oh my goodness, I skipped something, something important. Remember I said that this gives rise to this thing here. Well, this thing here is effectively phi rho integrated. And that gives rise in the case of in which the charge density of the particle is just Q times delta of y minus x. That just gives you Q times the scale potential at x and t. So this term came from that term there. What I skipped by mistake was the Hamiltonian for the field. So this is sort of the matter Hamiltonian, the field Hamiltonian, the part of it apart from the part involving phi is an integral v cubed x epsilon 0 over 2 e squared of x and t plus 1 over 2 mu 0 b squared of x and t. So that's the Hamiltonian for what we can call the transverse part, because here E is minus a dot now. Remember the part for phi, we've separated out, and it's turned into the charge or the distance term, and B, the B is always curl there. Notice because of the unfortunate notation in standard units, we have epsilon 0 in the numerator here, and we have mu 0 in the denominator here. And one of the amazing things about epsilon 0 and mu 0 is that the product is 1 over c squared. All right. This Q phi is, for the case of an electron around a proton, is minus q squared over 4 pi epsilon 0 x, and that's minus c squared over x, which you can also write as minus alpha h bar c over x, where alpha is c squared over h bar c, which is 1 over 137.04. Okay, so this really is appropriate to have questions. Are there any questions about this? Any mistakes you want to correct? All right. Okay, so what are the interaction terms? By the way, this P minus QA is really the mechanical momentum. So what's the interaction? Now, I noticed something that's really amusing, and it might be puzzling if you see it for the first time, so let me just point it out to you. See, P is canonically conjugate to X. Here's X. X is in the argument of the electromagnetic field, as well as in the argument of this. So it's an interesting expression. What is our interaction? So let me just point out what the free terms are. Of course, this part, the p squared over 2m and the q phi is what, let's in fact specialize to the case of photons interacting with a hydrogen atom, so we know that once we get beyond the hydrogen atom, the quantum mechanics becomes too difficult for us to do it exactly. It's terribly embarrassing. But anyway, p squared over 2m minus e squared over r, that's the hydrogen atom. We know those solutions. We worked them out earlier in the year, if somewhat rapidly. So that's the free Hamiltonian for us is going to be the Hamiltonian for the transverse fields, which is quadratic in the annihilation and creation operators, and the p squared over 2m minus e squared over x. That will be that. In fact, unfortunately, I don't know why I'm so sticky today. Your homework problem, the extra homework problem, would be to show that if you substitute this expression into here, you find that the Hamiltonian for the fields is sum over k, sum over r equals 1 to 2, h bar omega k, a sub r dagger of k, a sub r of k, plus a half. So that'll be the homework. Now, the extra homework problem and the assignment problem. Now, notice this 1/2 here. This 1/2, when summed over all of these, gives you a terribly divergent number. And that's one of the really embarrassing things about quantum field theory. And it's one of the reasons why we think maybe supersymmetry is right. Because in supersymmetry, you're able to cancel this 1/2 against a minus 1/2 that occurs when you quantize a spin 1/2 field, per Hamilton field. The extra term is a minus 1/2. So the worst part cancels. Okay. So in other words, our H0, our big H0, is that H0 matter is p squared over 2m minus e squared over r. H0 field, well, is just, maybe I'll put a 0 on this. H0 field is what I just wrote there. And so what's the interaction? Well, the interaction that's left is just the two terms that come from here, plus this if we put in spin, and usually we're not going to. So the interaction is minus q over m, a of x into dot p, and then the quadratic term, p squared over 2m, a vector of x and t squared. And this m should really be the reduced mass, but I'm not going to emphasize that. So it's really reduced mass. Now let me point out something that's another reason why people love the Coulomb gauge, and it's that, you see, I just wrote this once. I didn't write a p dot a term, whereas when you square this thing, you get p dot a plus a dot p. Okay? Why didn't I write them? The reason is that the divergence of a is 0, and so if you have p dot a minus a dot p, that's h bar over I divergence of a, which is 0. So that's the great advantage of the Coulomb gauge. Remember, p is h bar over I. We all happy? So this is a nice feature of the Coulomb gauge. That means that you can just write this as one term. All right, well, now I'm going to get a sip of tea, and then we're ready to actually consider the absorption of a photon by an atom. Let's see, I guess I skipped a little bit here in the algebra. I introduced these creation and annihilation operators. Let me just say what they do. The ground state of H0F is just a vacuum, and A sub R of K annihilates the vacuum for all K. Then the creation operator, AR dagger of K, on the vacuum turns us into one state, a state of that has one photon, momentum K, and polarization R, polarization index R. If we then have a dagger of, A sub R prime, K prime acting on the state KR, then we get a state that has K prime R prime and also KR. So this is a state of two photons. And one can think of this as, well, of course, they have to be symmetrized. Okay? So you can think of it as 1 over root 2, K prime, let me suppress the polarization, K prime K plus K prime, if you want. And so forth. As you add more creation operators, you get more particles. But in quantum field theory, we don't write down, we don't do this explicitly. In other words, we don't say, we just write it this way, that it's a state containing a photon with momentum K and polarization R, and another photon of momentum K prime and polarization R prime. Now, and in fact, if we go to the continuum limit, in other words, we're not quantizing inside some cavity, say, in a laser, but instead we're out in empty space, then the possibility that K and K prime would ever be exactly the same is zippo, and it's going to be completely ignored. But if we do let these K and K prime be the same, then you can see that A dagger, and let me suppress polarization again. A dagger of K on the state K would be, if you let K equal to K prime, these two states are the same. And so you have square root of 2 times 2K. In other words, the creation operator pulls out the square root of K. And in fact, I can do it also for the case of 3. Let me get my notes so because it's confusing. I couldn't find this in any book and had to work out. Must be in Fox, by the way, is the person who worked out much of this. This is called Fox space. At least he did it for scalar field. I suppose he probably did it for the argument. Anyway, suppose we've got a dagger K double prime on a state K prime. Then this is going to give us a state K prime, K double prime. Although some people like to say that if you started with K and then K prime, it really should be this way. I think that's the way Weinberg writes it. In any event, because it doesn't make any difference. So that's what the creation operator does. But now what happens if if K prime and K double prime are all the same, Then we have A dagger of K on this state, but this state now is square root of 2k equals this state, which is 1 over square root of 6. Then there's 6 identical terms, so there's a 6 here. So this is square root of 6. Well, this is in parentheses here, times 3k. So that tells us that A dagger of K on the state 2k is equal to square root of 3 to state 3k. And these are the harmonic oscillators. So in other words, for a single mode, the what you have is A dagger on the state of n photons is square root of n plus 1, n plus 1 for the particular mode. And similarly, A, if you work this backwards, you have, oh, I didn't say what A did over here. Well, A annihilates that, but A also, because of the commutation relations that we have there, A takes, say, take R back into the vacuum state. And moreover, for a given mode, A on n is square root of n minus 1. Okay? So we're all square root of n. In any event, the easiest, what as far as I know, everybody does is when you bring in the creation and annihilation operators, you then forget about how you did things with identical particles in quantum mechanics, and everything becomes subsumed into these commutation relations. And with these commutation relations, you never again have to think about these things. It may be a loss that you don't have to think, but there's enough things to think about. And the creation annihilation operators just make everything automatic. Okay, let me get a drink. I thought I was going to get further today, but I guess we've actually gone through quite a bit of stuff, despite the fact that we haven't mentioned it. Okay, so what's our, first of all, to do the interaction, to do the things of lowest order, we don't need this term. This term is higher order in Q. Q is essentially E, and E is small. The electromagnetic interactions are not weak, but they have a strength that's characterized by the fine structure constant, which is 1 over E squared, with alpha, which is 1 over 137. And so this term is always a small contribution as long as this term is not 0. If this term is 0, then of course you need to do this one. And when I say it always is the wrong word, because clearly if you were in a state in which the field A were very, very strong, then this term would be bigger than that term. So it's not fair to ignore this in favor of this in the case where A is huge. On the other hand, if we're talking about the absorption of a single photon by an atom, and we imagine that the photon is being exposed to a weak electromagnetic field, then this term can be neglected. And so if we just take the very simplest case, where we say V is equal to minus Q over M, A of X and T dot P, well, it turns out that to go to the interaction picture isn't that big a deal, because you see, in a sense, I've been writing here, I've been giving A time dependence all along. This is the time dependence that it gets from HF or H0F. So A has already the free field time dependence, so A is already in the interaction picture. One thing that just occurred to me that I would normally suppress, but just to be perfectly honest, A has x's here, and when you subject A to the whole Hamiltonian, including this part, which has a p squared in it, that p squared would act on these things, and I don't know, it may be saved by the Coulomb gauge condition, but I don't see it. I don't remember ever seeing that discussed in any treatment of this I've seen. So I'm going to ignore that for the moment. So what is V in the interaction picture? Well, it's going to be minus Q over M. A is already in the interaction picture because of this T dependence, the E to the I omega T on the creation and annihilation operators. But we need E to the I H0 matter T over H bar P E to the minus I H0 matter T over H bar. So this is the V in the interaction picture that we're going to use. And this H0 involves P squared over R. And as I said, A is already in the interaction picture because it has that free time dependence. Okay, so what is our time? Well, we're almost out. Let me just say that obviously what we're going to do is we're going to say that psi of t in our interaction picture here is the time-ordered product of e to the minus I over h bar integral from, let us say, 0 to t, vi prime to t prime, acting on psi 0 interaction. I don't know if we really need that. And in particular, in this case that we're talking about, in other words, this interaction picture stuff is kind of overkill. So the initial state with n photons of type R, momentum k, this is going to be, at time t, this is going to be effectively 1 minus I over h bar integral 0 to t. This is the lowest order computation, t prime dt prime times I n sub R of k at time 0. So this is where we'll pick up next time. We'll work this out.